Okay, so for today, um, the topic of equilibrium is very much a follow-up to kinetics. If kinetics is focusing on the concept that we are focusing on the speed of the reaction. So we're going from reactants to products, how fast is that happening, right? Now, we've been, for the majority of the year, we keep saying reactions are going from from reactants to products, and it's always one direction. That's a unidirectional kind of way that we're presenting it. But in reality, reactions will keep going back and forth, meaning it'll start with the reactants with no products. It'll make products. It'll get to the point where it establishes, it's as if like I have this container where like I swish the liquid inside that container and moves to one side, but it doesn't stay put on that side. It will kind of go back and forth. There is this back and forth that will happen until things are kind of evening out, right? So in reality, reactions happen in both directions. Reactants can form products, products can reform reactants, and it's a dynamic process. It's not a static process. It doesn't stop. It's a constant back and forth. Our focus now is on this idea of equilibrium. How do we know that both of these forward and reverse reactions, so forward would be the reaction going to the right for the product, and reverse will be going to the left, or producing the reactants once again. Our main standards for, see if I can show you that. The three main things that we want to focus on is what are the principles that helps us to predict which way the reaction is going, known as Le Chatelier's principle. How do we know that an equilibrium is already established? And then finally, how do we calculate this constant for equilibrium? All the math I'll reserve till next week. For today, it's really more of the concepts and the idea of Le Chatelier's principle. Sometime next week too, there's a lab where I'm collecting data to illustrate this whole idea. So just kind of giving you a preview that there's something related to, or we're doing some sort of like lab-based collection of data and graphing of that data. In this first slide, we're showing two different reactions, and the font size and the arrow size is done intentionally. We have the reaction on top, where it's hydrogen and fluorine creating hydrogen fluoride or hydrofluoric acid, perhaps. But the arrows are going in opposite direction. So one is making the product, and then the other one is taking the product and recreating the reactants, known as the reverse reaction. And as much as possible, the arrow sizes are the same. On the bottom, we have HCl and NaOH, our acid and our base, forming water and sodium chloride. But you'll notice that the size of the font of how it's written is smaller on the left, bigger on the right, and the arrows are also unequal sizes. With that, it's more of just kind of an introduction to this concept of equilibrium. Between the two, it seems like, or the most evident way of answering this question is, doesn't the top reaction seem to be pointing towards what we consider to be a process of equilibrium, a chemical reaction that is in equilibrium? Technically, it's a good representation, but it's not the best, because equilibrium really has two parts to its definition. And the best way that we could define it, so we're going to use two different graphs to help us with the definition of equilibrium. The graph on top, you'll notice that, so let me annotate this. It'll allow me, here we go. So the graph on top, it's letting us know that we have a reaction rate for the y-axis, meaning how fast the reaction is, and then time on our x-axis. In the beginning, the forward reaction, meaning reactants to products, it's there's a big change in the forward reaction. So you'll notice that the slope is pretty significant, and then it looks like it's slowing down to the point where it's almost like pretty flat. So we could say that the forward reaction is pretty fast in the beginning and kind of slows down towards the end. The reverse reaction is the same. Reverse reaction would be taking the products and then recreating the reactants. So it seems to be pretty fast in the beginning, but then it starts to slow down at the end. Now, looking at this graph, one thing we can infer from the graph is that whenever we're in equilibrium, it must be when the forward and the reverse reaction, how fast both of those are happening, it must be when they're equal to each other. The rate of reaction when they're equal to each other. I'll expand on that further in the next slide, but just kind of using this graph to help us understand the definition of what it means to be in equilibrium. The second graph, it's concentration on the y, and then we have time on the x. Let's say A is our reactant and B is our product. A is decreasing, so we're starting with a lot, and then you end up losing quite a lot of that reactant. But notice we didn't lose all of it. It kind of just like dwindled down to a certain amount, but didn't stay put after a certain, like it evened down. B starts with nothing, the product, and then we kept making of the products happening pretty quickly, and then it starts to slow down as well. Notice they're saying once we got to this point, it's now in equilibrium. So with that, can't we say equilibrium also entails when the concentration or the amount of our reactants in our products are no longer changing? Meaning, if the reactant, so our reactant is A, it was starting with a high amount, and then it's decreasing, and then it slows down. It didn't reach zero. It could, but in this scenario, they're saying it was used up to a certain point, but then eventually it just kind of held steady. The amount of it held steady. Let's combine those two. So now let's go to the next slide. Essentially what we're seeing with these two graphs, the definition of equilibrium is equilibrium has two parts. When the forward and the reverse reaction, how fast we're making the products and how fast we're recreating the reactants. When they meet up, when they are equal to each other, then we're at equilibrium. In addition, so it says here and, so it's not an or, it's this definition and this definition. The other component of it is when the reactants and products, when their amount have tapered down, like there's no longer changes to it. So that will be the secondary part of the definition. It says, and the concentration of reactants and products they eventually remain constant. The second definition is often the part where students get confused, or I would say there's some misconception on it, not necessarily confused. Because for many, they think that the concentration has to be equal. It doesn't have to be equal. It could be, like at the end, the amount of reactants and products might in fact be equal, but that's only one in certain reactions. The other possibility is, or the one thing we're really looking for is the amount no longer changing for the reactant, and is the amount no longer changing for the product? Not necessarily focusing on whether or not they're equal to each other. What we're looking for is a two-part combination, or it's a combination of these two. If the reaction, how fast it goes forward and reverse is the same, meaning the speed is the same, that's one. And then finally, when the amount of reactants and products are no longer changing, that's the other component we're looking for. If both are fulfilled, then we can say the reaction is in equilibrium. All right. There's an additional TED-Ed video that talks about this, using kind of like an animation to illustrate equilibrium. And there's a secondary one I posted in the Google Classroom that will that's focusing on my next topic, the next concept for today. But the key idea again is equilibrium is when the forward and reverse, how fast it's happening, is equal, it's one. And if your reactant and products are no longer changing in terms of their concentration, like it's consistent from that point on, we are now in equilibrium. The main thing we'll spend time on for today's discussion is this idea of Le Chatelier's principle. So let's say the reaction had reached equilibrium. It's now, the forward and reverse is the same, the amount has been consistent. But in chemical reactions, or let's say in the lab experiment, there could be some factors that could be changed to either favor going or forcing the reaction to like add some stress to that reaction. So meaning if I add stress, it's no longer in equilibrium. But if I add stress to it, then the reaction will most likely, or what the tendency is, it wants to reestablish equilibrium. It wants to go back to that point where the rate is equal and the concentration is consistent. So to do that, the tendency is um, to react based on the stress that's applied and to reestablish equilibrium. Le Chatelier's principle is basically saying, which way will the reaction go so we can go back to equilibrium? Will it go to the right, meaning to the product, or will it go to the left, meaning to the reactant? There is a third possibility we should mention. Third possibility in certain scenarios is there is no change, or like there is no side that's being favored. But the majority of the examples we're going to look at will focus on, or like the answers will be either going to the right or left. But I will show you an example where there is no favored side to this. The three factors we're going to focus on would be what will happen if we change the concentration, meaning add or remove. If we change the pressure or volume, actually, let me add that term. That would be helpful for us, pressure or volume. Because if we change the pressure, or if we change the volume, aren't we changing the pressure? Those two are definitely related to each other. They are technically inversely related to each other. And then finally, temperature. Can we add or remove heat? And if we do that, how would it affect equilibrium? Prior to kind of going through all these different Le Chatelier principle example, we need some sort of a reminder of some key ideas. If the reaction, so this is not Le Chatelier's first, this is just like a way for us to clarify some things. If the reaction says that, or if we're given this reaction where it's A that's gas, B plus gas, and then when those two combine, they need heat. Heat is being added to them. They're able to make a product of AB that's also gas, some generic formula here. Based on what we can see in this reaction, aren't we dealing with an endothermic reaction? So endothermic is when heat is being added. So heat is on the left side. If it was exothermic, this word heat would be a product. It would be on the right side of the equation. So just keep that in mind for those of you like taking notes, or if you're just paying attention, just that's perfectly fine. Just make sure to remember that if the problem states that it's endothermic, heat is acting as if it's a reactant. If the problem is stating it's exothermic, heat is acting as if it's a product of the reaction. The other thing we have to account for with dealing with Le Chatelier's principle is counting the number of gases. It turns out that when dealing with change in pressure and volume, the main thing that's really being affected by that is how many gases you have on the reactant side versus how many gases you have on the product side. So in this example, we have 1 mole of A, 1 mole of B, making 2 moles of gas on the left side, but there's only 1 mole of AB on the right side. So between the two sides, it looks like we have 2 moles of gases here and 1 mole of gas there. So pointing it out for a reason, because when we get through each of the examples, that could be something we have to factor in making our decision. Finally, the last one that we need to factor is, if we have 2 moles of gas here versus 1 mole of gas there, isn't the left side occupying more space? Because there are more, since gases tend to kind of be far apart from each other, if I have 2 of this versus 1 of that, the right side is only occupying half the amount of space compared to the left side. So that's another thing that we have to consider: how many gases and how much space they're occupying. All right, here's the first example. So the way this direction works is that I'm going to show a scenario, and then based on that scenario, I mean, on your end, ideally, if we were together, I would have you do like work in pairs, make a decision, and then we'll check your answer and explain every single one of them. But and we tried to do in the earlier period like a group thing. It logistically didn't quite work. So what I'll do is I'll go through a scenario, give yourself an opportunity to make a decision. You can write it down or just in your head, and then I'll discuss the answer. And we'll do as much of this. It's about 10 that we can get through throughout the session. All right, let's start with the first one. So we have that same exact reaction where we have A plus B, and it's an endothermic reaction. How do we know that? Heat is being added, meaning in order for these two to be able to combine together, they needed heat from somewhere, from an outside source. So disturbance number 1 says, what if we add more products? Meaning I'm adding more on this side. So imagine you're on kind of this seesaw, and it's a back and forth, but for the most part, it's pretty even, right? Or like the back and forth is happening consistently, that for the most part, like if I'm taking a snapshot, it seems like they're pretty even. One thing that's going to happen with this scenario is if I add more on the product side, there's too much now on one side. So the tendency is if there's too much here, the Chatillon's principle says it wants to get away from the source of stress. So too much here means the reaction will go to the left. So our answer for the first scenario is it will go to the left. It will proceed away from adding too much of that concentration. Too much of the products, it will go this way, away from the higher concentration. All right, scenario number 2. What if we add more heat to this endothermic reaction? So keep in mind, it's endothermic, so the word heat is on the left side. If I add more heat, it's as if I'm adding another reactant, like I'm making the left side a bit more crowded in a way. So if that's the case, the tendency is it wants to go to the right, away from the source of that disturbance. So adding more heat, because the reaction is endothermic, meaning the word heat is, and I should point out, in the actual chemical reaction, the word heat doesn't show up. Like I'm including it here to help us make sense of this whole idea. But technically, it would be A plus B makes AB. That's all really we're going to see. And then in the description, it might indicate that it's endothermic. But to help you visualize that, because it's endo, I added the word heat to kind of give you a hint that it acts as if it's a reactant. So now, disturbance 2, because we are adding more on this side, the tendency is it wants to go away from that side, so it will lean towards or lead towards the right side, the product side. Scenario number 3. What if we increase the pressure in the container that contains this reaction? Every time there's a pressure or volume scenario for Le Chatelier's principle, you're going to have to, it's best to picture a container that's, let's say this big. If I increase the pressure, one way I can go about that is by making the container smaller. So imagine like starting from a bigger container to a smaller container. I don't have a lot of space. So if you don't have a lot of space, because you increase the pressure, meaning you decrease the volume, thus increasing the pressure, then the tendency, based on Le Chatelier's principle, is to go to the side where there's less moles of gas. So if we increase the pressure, we want to go away from the side where they're taking up too much space. So the tendency here is to go to the right. And the rationale for this is the left side, there are 2 moles of gas. They're taking up a lot of space. The right side, there's only 1 mole of gas. They're not taking up as much space. So if we increase the pressure, there's not a lot of space, then the tendency is to go to the area, the side where there is less gas, and that would be to the right. Right. Disturbance number 4. This time, instead of adding, we're removing. So in this scenario, they're saying we have a different reaction now, but still generic. C plus D makes CD. What if we remove C? So C is being taken away. But if this was already in equilibrium and we were removing one side, then to go back to equilibrium, whatever is being removed has to be replaced. So the tendency for this is by removing something on this side, the reaction tends to go to the left. Like in this case, it tends to go to the side where it wants to replace what's being lost. So if I'm losing C, then we got to replace C. And to do that, we have to take some of the products, break them apart to make C again. So the answer is to the left. Disturbance number 5. This is a cooling down question. So in this scenario, they said, what if, I meant to, so I'm gonna fix this right now for the other classes. Paste and erase this. We can see the answer already, but I meant to like show you the question first before I show you the answer. So let me erase this. All right, originally we would have just seen this, C plus D, and then it would just say, what if we cool down this reaction? Since we've seen the answer. First hint there is exothermic. So if it's exothermic, the word heat must be on the right side. So exo meaning it's getting produced, it's leaving the system. So it must be on the right. Now, the tricky part about this is it's a cooling down rather than heating up. We're removing heat. So if heat is getting removed, I'm taking away something from this side, it's gonna have to be replaced. So if I remove something here, remove heat, it needs to be replaced. The tendency is the reaction will take the reactants, make more of the products, because every time they do that, they're producing heat. Therefore, we're able to replace whatever was getting lost, the heat that was getting lost. So the answer is that it will go to the right. All right, disturbance 6. Still the same reaction, but now it's a pressure question. Remember that with pressure, we count gases. We have 2 moles of gases here and 1 mole of gas on the right side. But this time around, they're saying, let's decrease the pressure. Here's our visual. Here's your container. If I make, so let's say this is our starting point. If I make the container larger, am I not giving it more space? So if there's more space, there is less pressure in there because there's more space for the molecules to move around. The problem though is in order for us to get back to equilibrium, because now we have more space, we need to occupy that space with other gases. So a decrease in pressure tends to go to the side where there's more moles of gas. Let me repeat that. Decrease in pressure tends to go to the side where there's more moles of gas. In which case, our answer for this, if I can get this right, is to the left. So the rationale for it is by decreasing the pressure, there must be an increase in volume. And if there's an increase in volume, there's space to be filled up. And what we can do is occupy that space with the side of the reaction where there's more gases available for us. So they can take over that space and reestablish equilibrium. Disturbance number 7 is related because now it's about volume. I know we kept talking about pressure, but pressure and volume are interrelated to each other, right? So here's the visual. They're letting us know, here's our container, but we are making it smaller, decreasing the size of that volume. Now, decreasing the size, isn't this an increase in pressure? Because now there's not a lot of space. So unlike the previous question, this one they're saying, we don't have a lot of space. We can't take up too much, the gases can't take up too much space. So the best scenario is to go towards the side where there is less gas. So let me repeat these last two because they are related. If you are decreasing pressure, it's going to go towards the side where there's more gases. If you are increasing pressure, it's going to go towards the side where there are less gases. That's kind of like a key takeaway, at least based on this part of Le Chatelier's principle. All right, now we're almost done. It's a couple more left here. In this scenario, they're saying, what if we increase the temperature if the delta H is negative 100 kilojoules per mole? So now the word heat is not showing up, but our clue here is negative 100 kilojoules per mole. If the delta H is negative, isn't it exothermic? And if it's exothermic, the word heat must be on the right side. So it's still the same disturbance. So they're saying, let's increase the temperature if the delta H is negative. And if delta H is negative, it's exo. The word heat is over here. If I add more heat, because it says increase the temperature, then, wait, let me fix this. Adding more heat, not to the right, just caught an error here, to the left. Because the idea here now is if it's exo, the word heat is on the right. And if we're adding more on that side, it wants to go away from it. So that will go towards the left side. So that's scenario number 8. All right, number 9. We have a different reaction. So this one is 2 moles of gas here, 1 mole of gas there. Again, increasing pressure means you want to go from the side where there's too much gas to the side where there's less gas. So the tendency for this is, oh, I see. I think my answers got switched from the 2 slides. This is the one that goes to the right. All right. The idea, did I change the scenario? It looks like I changed the scenario. Okay, let me fix this because it says decrease, increase, and then it changes to decrease. All right. If we increase the pressure, we are going to be going to the right because that's the side where there's less moles of gas. So that's something we heard about earlier in a different example. Let's finish up with the last one here. So now they're still increasing the pressure. It's still the same scenario. But one thing that changed here is this. The fluoride is now a liquid, or not fluoride, but element F, whatever this compound or element is. It's a liquid. And because of that, liquids and solids, they have a fixed kind of a density to them. So, or for relatively fixed for liquids. And because of that, they're not really widely affected by the pressure that much, especially in a smaller kind of case scenario of a chemical reaction. So pressure is really dependent, we really just focus on gases. We count the number of gases. So that tells me there's really only 1 mole of gas on the left side and 1 mole of gas on the right side. If they're equal, then it doesn't matter what change we do with pressure, increase or decrease, if they're equal. And the answer here is there is, if it shows up, no side is favored. So this is the 3rd scenario where it's not neither right or left. There's nothing that's going to affect, or changing the pressure doesn't affect the balance there. Because the idea is that we have equal moles of gas on the left side versus the right side. All right. The best way to really make sense of Le Chatelier's principle is to hear as many examples. That's why I try to at least get through like 10 of them here and give you some rationale about each one. I posted a video that on our Google Classroom. First one's a short one about just what is equilibrium, but the second one deals more about different examples of Le Chatelier's principle. So please make sure to watch that. And then the last reminder that I have as we finish up today is to make sure that you finish those 3 kinetics practice problems. There was a Poggio for collision. There was a second thing was silver clock. And then the third thing was the graphing. All 3 are due on the day of your quiz, which would be Thursday for period 5 and 3, and then Friday for periods 2 and 4. All right, I'm gonna stop here and we'll go through questions.